Hello, welcome again to yet another lesson. This one is 13.3 and we're talking about properties of logs. Now, what we did earlier, 13.1, we talked about basics of exponents and exponential functions. In 13.2, we talked about log functions, what log functions are, their x-intercept, their y-intercept, asymptotes, graphing them. And then we also learned how log functions and exponents are related to each other. Related. Well, they are inverses of each other, which means one cancels the effects of the other. And exponent cancel the effect of log and vice versa. 13.3, we're talking about properties of logs. Before I even start with that, I want you to know two things. Number one, constant e. Now, e is a constant and its approximate value is 2.71828, so on and so forth. It actually never, it continues forever. Kind of like pi, which continues forever. So this is an irrational number. And why is this important? It is kind of used in exponential growth, whether it's population, biology questions, viruses, bacteria, how they multiply and divide. So you don't have to get into the detail, but just know that E is a constant number and that's about the value of it. The other thing you want to know is what is Ln? I'm not sure if you paid attention, but on your calculators, TI-83, 84s, and even on Desmos, we have a dedicated button for Ln. What is Ln? Ln is actually called natural log. It's also called Euler's number. He was the one who came up with it. And so it's called Euler's number. What does it mean? This is what it means. It's actually log. For example, if I have log to base 2, let's say, of x, right? Log base 7 of x, so on and so forth. Now, clearly in the first one, base is 2, over here base is 7. When the base happens to be e, this special number that we just discussed, let's say we have log base e of x, then we generally, you're not gonna see this basically. You're gonna see it rewritten as ln of x. So ln of x automatically means that it's log, but the base is e. That's the only difference. I mean, actually, there's no difference. It's just we're treating it special. Why are we treating it special? Because e is a irrational number that kind of continues. Okay, so knowing those two things, we will proceed. By the way, do also remember if you have log of x, let's say, with no base given, we discussed this last time, that that base is always 10. It's an invisible 10. It's assumed that that's what it is. And that's the other button that you see on your TI-84s or 85, oh sorry, 83. That's the other button you see. So you'll see two dedicated buttons in the calculator. One is for log and one is for ln. So this is automatically base 10 and this means it's automatically base e. All right, so let's move on with the properties. Topic number 1. What are the properties of logs? I have 3 for you. Number 1, the first property says the log of a product equals the sum of the product. The log of a product is the same as the sum of logs. What does it even mean? This is what it means. If you have log base A of a product, m times n. Now, m and n are two different numbers or two different expressions. If they're being multiplied, then the log of the product of something is the same as the sum of the logs, individual logs, log base A of m and log base A of n, sum of the products. Now the base obviously is going to stay the same because they were together to base A, whatever that base is in the question. Second property is about the same except that the log of quotients, if you have division instead, is the same as the difference of logs. Instead of sum, it's difference. Example, if I have log to base sum A, but if I have a quotient of two expressions, m divided by n, then that's going to be the same as log m base A minus log n base A. Base has to stay the same. And the third property is very important. It's very easy, but very important, and we're about to use that in a bunch of questions. Log of a power. Log of a power, read it carefully, equals the product of the power and the log, equals the product of the power itself and the log. Example, let's say we have log m base a, but let's say m is raised to the power of r. There has to be a power, right? Once we do have a power, it can actually be rewritten as the product of the power times the log itself. The r times log m base a. But basically this power can be just brought here. If you look at it that way, it's so much easier to look at it that way. You can take that power and basically drop it in the very front of the log. All right, these three properties, and I'm going to show you a bunch of examples that uses them. All right, that is beautiful and gorgeous. Let's begin. Example 1. Now there are two sets of examples. Number 1, we are rewriting the log, expanding the log or shrinking the log, right? Log or logarithm expression as a sum or difference of log, which means we're expressing, which means every time we'll be given this type of format and we will expand it to either addition or subtraction. And then we'll show you backwards. Example 1. Let's say I have log base b, whatever the base is, times log of x times y squared. Log base b, xy squared. Now x is automatically being multiplied to y squared. Keep that in mind. It's x times y squared. Obviously, we do not write that squared. Now this one's telling me write the log expression as a sum or difference of log. Now how do I know if it's sum or difference? I'm going to follow these properties. If you have a product, then you can write it as the sum of the logs, just like this, and that's what we're going to follow. This is the first one, which means I can rewrite this as the sum of log b of the first one, which is x squared, not just x, plus log base b y squared. So I rewrote that product log as sum log. And once I have this, I'm kind of actually not done. You know why? Because within this property, there's another property built in. This first one is simplified all the way, log base b of x. Plus, now you see that power here? So I can actually use this third property, which is the power property. That 2 can be brought to the very front. 2 log of y base b. And now I have expanded it as much as I could. Log base bxy squared. Okay, let's look at another example, and you cannot expand that anymore. Let's look at another one, log base b, and I have x squared square root of y. Yeah, let's just keep it that way. So what do I have to do? Again, the directions are the same, right? Log expression, this is the log expression, as a sum or difference of log. Now, how do I know if it's a sum or difference? I'm going to identify that this is the product of x squared and root y. You know what? I hope you remember that roots are basically fraction powers. So this is basically y raised to the half power because it's a square root. So one more time, this is log of the product of x squared and y to the power of half, which means I can use the product property, the first property. I can rewrite this as a sum of log base b of x squared, log base b of y to the power of half. And how do I know am I done? Well, I see powers there. Anytime you see powers, you can actually bring it here. Here's a power, I can bring it to the front. So we have 2 log b x plus half log of y base b. Now there's no powers. I don't see any products either. This is just x, this is just y. So I know I've broken it down as much as we could. All right, I'll show you another one. Let's say log base 4, 4x squared. And again, the question is the same. Write this log expression as a sum or difference of log. How do I know this is sum or difference? Well, this is the product, so I'll have to use the first property. Hence, it can be rewritten as the sum of, well, this is the product of 4 and x squared. And that's what I'll break it down into. Log base 4 of 4, and then log base 4 of x squared. Now, we are not done because both of these are numbers, so I can actually find answer to the first one. How can I find answer to the first one? How do I know what's the answer to this? This comes from our previous lesson, which said, think about this, evaluate. That was 13.2, evaluate. How do I read this? 4 raised to some power equals 4. Start here, go here, and then go here. Basically make a circle. And the minute I rewrite it as an exponential problem, hopefully we all know that 4 to the first power is 4. So this simply equals 1. This part simply equals 1. Plus, how do I know the next one is simplified? Well, I see a power, and the third property says if you see log of a power, then you can bring the power in the front. So 2 log of x to the base 4. And now I know this has been simplified as much as it could be. Interesting, right? Just off of those 3 properties, a lot can be done. I haven't shown you any division ones. Time to show you that. Log. Actually, this one is natural log ln. We have root 3x over 7. Pay attention to this one. All right, so first of all, it's ln, natural log. And no big deal, as I told you, this simply means it's log base e of that whole thing. Okay, you can think of it that way. So, do I expand it or what do I do? Well, this looks like division, right? It's this over this. So let's apply property number 2. When we're dividing, we can rewrite it as the subtraction of the numerator and log, natural log here, minus natural log of 7. And how do I know I'm done? Well, this is, remember, this is square root, which means 3x is raised to the power of half. And the minute I see power, it's time to use the third property that power can be brought in the front here. So half natural log, I have 3x minus natural log of 7. And guess what? We're still not done. You know why? Because I still have log of products, 3 times x. Anytime we have that, this can further be broken up. Well, don't forget the half. Half is half. This can be rewritten as the sum of natural log 3 plus natural log x minus, don't forget there's a natural log 7 sitting over there. And now if you notice, do we see any powers? No. Do we see any product of logs or log of a product? Not really. I see log of 3, log of x. These aren't products anymore. And I see natural log of 7. So no products either. Do we see any quotients? No quotients either. So none of those properties can be applied anymore. We have simplified it as much as we could. So natural log root 3 times x over 7 equals all that. You know, I feel like showing you one more example, and then I'll move on to backwards type of questions. Natural log x minus 3. And I'm still in the same category, so the instructions are in dark blue here. Write log expression as a sum or difference of logs. We're following the same pattern. Now, how do I know whether I write it as sum or difference? Same thing. After the log sign, this happens to be the natural log, I see x being multiplied with x minus 3. right? So we have product here. Anytime we have product, that can be rewritten as sum, natural log x, natural log x minus 3. Okay, now do I see any powers? No, so there's no need to use property number 3. What else do I see? It looks like that's it. I don't see any power here. Yeah, honestly, I think that's it. I have separated it. So this was topic 2. All right, let's do backwards now, which means write log expression as a single logarithm, so just the opposite. Write logs, which means it's going to be given, hold on, log expression as a single log or logarithm. There we go. Which means we're doing backwards. Kind of like we'll be given this and we have to shrink it back to get that. That's exactly what we're doing. Now let's see what does it look like. Let's start with example 1. I have 2 natural log 8 plus 5 natural log of x. And I have to combine it into a single expression. Now how do I combine? I see that this is addition, right? Which means addition, if you look at the 3 properties again, if you see addition, which means this can be combined as the product, or sorry, log of the product, backwards. Okay. Which means I can rewrite this as, and again, both of them are natural logs, so log. Oh, you know what? I have to take back a step here. Can't use that until, because of the 5 and the 2. So can't use that. Instead, we would use property 3 first. You see that 2 here? This can be moved back to the power. Same thing with the 5. This needs to be moved back into as a power. We're using property number 3 here. Before I can even do 1, I have to do 3. Right? This R, those were my 2's and 5's, which means this can be brought back here as power into this one. So this is natural log 8 squared plus natural log x to the 5th power. Now that I just have the logs and nothing before it, now I can look at it as being added, and because this is addition, it can be converted back to the product. 8 squared times x to the 5th. One more step, 8 squared is 64, x to the 5th. And I have combined it to a single log expression. And it might look weird, but it just needs practice, and you need to look at more examples. Here I have another one. This is a long one, slightly long. Log of 5 base 2 plus log of x base 2 minus log of 3 base 2. Interesting. It's like, okay, can I combine that to a single expression? So we'll start from left to right. As you go from left to right, we see that both of them are logs. There is no number here, so we don't have to take it to the power. Both of them are log base 2, and this is addition, so I could combine them into product. And they both are log base 2. Product of 5 and x. Right? Then I still have minus log 3 base 2. Now when I look at it, now I have a subtraction log problem. Both of them are logs to the same base. Now subtraction, working backwards, we're going to use property number 2. When we have subtraction, we can combine it to a quotient problem with logs. log base 2, 5x over 3. And I don't see any exponents, so that doesn't have to be considered. And I have compressed it to one single log expression. Example 3. This one is even more interesting. Natural log of 2x. This will be my second to last example for this topic. Natural log 3. And same instructions, write the log expression as single expression. So I do see subtraction here, which means I should be able to convert it to quotient problem. But before I can even do that, I see this sitting on the outside, which means this can go as a power. So natural log 2x minus natural log 3. Oh, actually, I couldn't do that because I just realized if I put that 3, do I raise all of this to the power of -2? That does not look right to me. So I need to tackle parentheses first. I did not realize that there are parentheses there. So -2 will stay here. The inside, it needs to be taken care of first, which is a subtraction log problem with the same log, ln, natural log, that can be converted into a quotient problem, 2x over 3. Now that I've combined it, now this -2 needs to go here as the exponent. So we have natural log 2x over 3 raised to the power of -2. Interesting, we actually have a negative power. Now back again to lesson 13.1 where I told you the property of what do we do when we have negative exponents? Kind of like this. As if we have negative 5 raised to the -2nd power, it's basically 1 over 5 squared. So if the negative exponent is in the numerator, you can simply change it to positive by bringing it in the denominator. And vice versa works as well. If you have a negative power in the denominator, you can bring it to the numerator and convert it to a positive power. And now there's 1 in the denominator, we don't have to write that, right? So now if you look at this, both 2x is raised to -2nd power, and then 3 is also raised to -2nd power. So I'm going to swap their positions and make them positive power. If this comes in the denominator, turns into +2, and this goes in the numerator, turns into +2. 3 squared we know is 9. 2x squared is 4x squared. And I have combined it to one single log expression. This is the same as that. If I were given this as the problem, I would have continued backwards to be able to get that. All right. I said this is the second to last example. I'll show you one more and then we move on to our last topic for today. This one is equally interesting. 1 plus 3 log x base 4. What do I have to do? I have to again compress it to a single log function. Now if you look at that one doesn't even have any log. I mean I can take the 3 and I can put it to the power. Let's do that. 1 plus log x base 4, x to the 3rd power base 4. Okay, I got that, but then I'm like, okay, what do I do next? Because there's a 1 there and 1 does not even have log. Now the interesting part is that you can rewrite 1 as a log problem. I can convert this to a log problem. Now it has to be log to base 4. It has to be the same log, right? So I can actually apply property to it. So I do this, but how do I get a 1? Like log base 4 of what will equal 1? Because I want it to be equivalent to 1. Same thing, you have to use you have to be able to convert from log to exponent, exponents to log. This question is saying 4, right? Start here, 4 to the power of 1 is what? We all know it's 4, right? 4 to the first power is 4, which means this has to be 4. So log 4 base 4 is equal to 1. That's actually another property. What I'm trying to say is if the base and the number right next to it is the same, the answer will always be 1. Let's say log 10 base 10. What does that equal? Well, think about it. 10 to what power would equal 10? 1, right? Yeah, so anytime these two are the same, the overall answer for that log problem is 1 plus log base 4 x to the third. Now the trick is, why did I use 4? Why did I pick 4 as the base? Because the next term had 4 as the base. That's why I picked 4. And because I picked 4 here, I had to make this also a 4, because 4 to the first power will be 4. Okay. Okay, let's continue. Now that they both are logs to the same base and it's a sum problem, which means I can combine it to a product problem. 4 times x to the third power. Now it's all combined and compressed into one term. All right. And the last concept here, which is number 4, is change of base. This one is very interesting and very useful. Let me tell you why this is useful. Again, consider that on the calculator you'll have two buttons, either the natural log or the log so far, right? This is automatically dedicate. This means base 10 by default. This means base E by default. So if we have something other than base 10 or base E, we have other means to find the answer without using calculator until the very end. Now Desmos does have it. You can change the base. TI-83s, 84 also have it somewhere hidden, programmed. Let's understand it, and I can always show you how to do it on the calculator as well. Change of base is a very simple property. All it says is, if, oh, there it is. If you have log to any base, A, M, okay, and you're not able to handle that base A, let's say that base is besides 10 and E, that's the point, it's besides 10 or E, some other base, 5, 6, 8, 9, 11. This problem can be converted into a quotient problem. Log to any base, you can change it to any base, M, divided by log to the same base B of A. This is the formula that helps us change the base to any base we want. For example, if I have, let's say, log base 3 of 21, let's say, okay, and I'm like, oh, I don't have Desmos, so how do I even evaluate this, because the log button is base 10 and this one is base E, but I have base 3, so how do I use the calculator? Well, you can simply rewrite this as log. You can change, you can pick your base. I mean, let's pick 10 of 21 over log of the same base 3. Now both of these are on the calculator. You can simply punch in log 21 divided by log 3 and it'll give you a number answer. For example, let me show you an actual example. Let's say we have log of 89, base is 5. Right? So you're like, oh, I can do it on the calculator, but oopsies, both the buttons don't really work for base 5. So what can I do? I can convert it both to base 10. Base 10. So, but 89, so log of 89 base 10 divided by log of 5 base 10. And now this is calculator ready. All you have to do is press log button followed by 89 divided by log button followed by 5, because that log button is by default base 10. And once you do that, this will be a long number, 1.949 yada 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 long number divided by 0.69 long number, which almost simplifies to approximately 2.788. So we can use calculator. There's just a little trick that we can change the base. Let me show you one more example for the same kind of concept, and then we'll be good to go. Let's say we have log a weird base 7 of 63, let's say. So what is the question even asking me? I have to evaluate it, right? It's basically asking me 7 to what power equals 63. Make a little circle. 7 to what power equals 63? Well, the answer is going to be long decimal n. So think about it. 7 to the first power is 7. 7 to the second power is 49. And the minute I go to 7 to the third power, that is 49, 7, 30, 34, right? 343. And we were looking for 63, so that's somewhere here between 2 and 3. This answer is between 2 and 3. I got that part is between 2 and 3, but then that base 7, there's no dedicated switch to it, so I'm going to quickly use the change of base property. I'm going to do log 63 over log 7. Put it in the calculator, and it will, let me see if I have Desmos open. Log 63, log 7, right there. 3 divided by log 7. There we go. 2.12915, 2.129-ish. 2.129-ish. Correct. And we knew it was between 2 and 3, and it is obviously more closer to 2 than 3. All right. So what is the bottom line here? We learned 3 properties of logs. That this always worked with logs, 3 properties, and based off of that, we converted log expression to sum or difference logs, or backwards. We were given sum or difference, and we combined it to one single log. And the last thing we did was how to change the base so we can use calculator to find log values or evaluate logs. All right, that is it for tonight. I will see you in class. Bye.